Imagine two identical twins. One embarks on an extraordinary journey through space and time. When the traveling twin returns, they are no longer the same age. This is the twin paradox. It sounds like science fiction, but it's a genuine prediction of Einstein's physics. His theories revealed that time is not constant. It can stretch and squeeze. This paradox has puzzled and fascinated scientists for decades. To understand it, we must explore special relativity, where our common sense about space and time gets twisted. So, let us begin our journey into this amazing realm. It is a journey into the very fabric of reality. In 1905, Einstein introduced his special theory of relativity, revolutionizing our understanding of space, time, and motion, resting on two fundamental principles that challenge the conventional wisdom of the time. First, the laws of physics are the same for everyone moving at a constant speed in a straight line, no matter where they are in the universe. Think of a smooth airplane journey. You don't feel different from someone standing still on the ground, as long as the motion is uniform. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. This speed is approximately 299,792 kilometers per second, an unchanging cosmic speed limit. These principles lead to extraordinary conclusions. Space and time are not separate entities but are interwoven into a single fabric known as space-time, which can stretch and bend. This space-time can be warped and distorted by motion and gravity, key to understanding how time behaves differently for different observers, a concept that has profound implications for our understanding of the universe. One startling consequence of special relativity is time dilation, where time passes differently for different observers based on their relative motion. This means that if you are moving at a high speed relative to someone else, you will experience time more slowly than they do. A moving clock appears to tick slower to a stationary observer. This phenomenon has been confirmed by numerous experiments, including those involving high-speed particles and precise atomic clocks. Imagine a light clock on a speeding train. To someone on the train, the light pulse goes up and down. To someone on the platform, it travels a longer diagonal path. This difference in the path length is crucial to understanding why the clock ticks slower. Since the speed of light is constant, the moving clock ticks slower from the platform observer's perspective. The faster the train, the more pronounced this effect. This is not just a theoretical concept, but has practical implications in technologies like GPS. If the train approaches the speed of light, time on the train slows dramatically for the observer. This applies to all measures of time, including biological aging. So, if you were on a high-speed journey, you would age more slowly compared to someone on Earth. On the train, your heart would beat slower, and your thoughts would process slower relative to someone on the platform. This effect, though minuscule at everyday speeds, becomes significant at speeds close to that of light. This stretching of time is essential for understanding the twin paradox, a thought experiment that highlights the strange and fascinating nature of time dilation. Now let's set up the twin paradox scenario with twins Stella and Astro. Stella stays on Earth while Astro travels in a spaceship at near light speed. From Stella's perspective, Astro's time passes much slower due to time dilation. After 50 Earth years, Stella expects Astro to be significantly younger. If Astro experienced only 10 years, he'd be 40, while Stella is 80. The paradox arises because Astro can consider himself at rest, with Earth moving away and then returning. Both twins have valid arguments based on relative motion. Why should one twin's perspective be privileged over the other? This puzzle baffled many, but there is a resolution. The key to resolving the twin paradox lies in acceleration, a crucial factor often overlooked. Special relativity deals with uniform motion, but Astro's journey involves acceleration and deceleration, which are pivotal in understanding the age difference. Stella remains in a single inertial frame, experiencing no change in velocity, while Astro changes frames multiple times. Astro feels forces during acceleration and deceleration, breaking the symmetry of their experiences and leading to different aging rates. General relativity, Einstein's broader theory, is needed for a full analysis, but even within special relativity, the asymmetry is clear and undeniable. The twin paradox is not a paradox but an illustration of relativity, showing how time can differ based on motion. Time is relative to an observer's motion and gravitational field, making it a flexible and dynamic concept. Astro will indeed be younger than Stella upon his return, a fascinating outcome of their different journeys through space-time. This scenario highlights the intertwined nature of space and time, challenging our intuitions but confirming the fundamental workings of our universe.